Hey there! Today, we are going to unlock a really powerful tool in algebra. We're talking about writing the code for things that grow or shrink by multiplication. This is how we can model everything from a growing population to the value of a car. So let's just dive right in.
Okay, so check out this data for a minnow population in a pond. It starts at 1,000. Then, a year later, boom, it's at 1,200. Now your first thought might be, oh, that's easy. They're just adding 200 minnows. But hold on, look at year 2. It's 1,440. That's a jump of 240, not 200. So that tells us something really important. The pattern isn't adding the same number over and over. It's something else. It's multiplicative. And our job is to figure out the exact rule behind it.
All right, so here's our game plan for today. We'll start with the basic formula, then we'll break down how to find its two key parts, A and B. After that, we'll build the whole function, talk about a super common mistake to avoid, and then you'll get a chance to try one out for yourself. Let's get to it.
First up, let's get familiar with our main tool for all of these problems, the exponential formula.
Okay, this right here is our blueprint. Y equals A times B raised to the power of X. So, what do all these letters mean? Well, A is the initial value. That's our starting point, right when time is 0. B is the constant multiplier. Think of B as the engine of the whole thing. It's the pattern that repeats, whether it's growth or decay. And X, that's our input, usually time or the number of steps. Really, our whole mission here is just to figure out the values for A and B.
All right, we've got the formula. Let's start with the first piece of the puzzle, finding A, that initial value.
Finding the initial value, A, is usually the easiest part. All you have to do is look for the output, the Y value, when the input X is 0. So if we look at our minnow table, at year 0, what's the population? It's 1,000. That's it. Our A is 1,000. Simple as that.
Okay, A is done. Now let's move on to the trickier part, finding the pattern, our B value.
So, since we already figured out the pattern is multiplicative, our strategy has to involve, well, multiplication or division, right? To find our multiplier B, we're going to calculate the ratio between our Y values. And what that really means is we're just going to divide a term by the term that came right before it.
Okay, let's actually do this. For our first pair of numbers, we'll divide the year 1 value, 1,200, by the year 0 value, which was 1,000. And what do we get? We get 1.2. Now here's the most important part. It has to be a constant multiplier. It has to be the same every single time. So we have to check the next pair. Let's see. 1,440 divided by 1,200. What does that give us? It's also 1.2. Okay, looking good. Let's do one more just to be absolutely sure. 1,728 divided by 1,440 is, yep, 1.2 again. The pattern is consistent. We've found it. Our constant multiplier, B, is 1.2.
We've got A, we've got B, we have everything we need. It's time to put it all together and build our function.
So let's recap. We found our initial value, A, is 1,000. And we just calculated our constant multiplier, B, is 1.2. Now, we just have to plug them into our blueprint. Y equals A times B to the X. So our final function that perfectly describes the minnow population is Y equals 1,000 times 1.2 to the power of X. And there it is.
Now, before we move on, I want to talk about a really common mistake. It's a trap a lot of people fall into, and I want to make sure you can see it and avoid it.
Because when you see that first jump from 1,000 to 1,200, it is so tempting to think, wait, isn't the pattern just adding 200 each year? This is the classic mix-up, thinking linearly when the pattern is actually exponential.
And you know what? To be fair, for that very first step, you're not wrong. 1,200 minus 1,000 is 200. It seems to work, and that's exactly why this is such an easy trap to fall into.
But look what happens on the very next step. The difference between 1,440 and 1,200 is 240, not 200. See? The add 200 pattern breaks immediately. This is our proof. It's undeniable evidence that this function is not linear.
So here's the big takeaway. The thing you absolutely need to remember. Linear functions have a constant difference. You're adding or subtracting the same amount each time. But exponential functions, they have a constant ratio. You're multiplying or dividing by the same amount. When you see a table, your first job is to figure out which one it is.
Okay, let's try a different kind of problem, this time from a word problem instead of a table. So Marshall bought a car for $25,000 and it depreciates
That's just a fancy word for losing value by 10% each year. That phrase, 10% each year, is a giant clue that we're dealing with an exponential function.
First up, let's find our A. What's the initial value in this story? Well, it's the price Marshall paid for the car right at the beginning, right? So that's $25,000. Easy enough. Our A is $25,000.
Okay, now for B. This can be a little tricky when you're dealing with percentages, but here's the process. You always start with 100% of the value. Since the car loses 10% each year, we subtract that 10%. So 100 minus 10 is 90%. That means 90% of the value remains each year. Now to use that in our formula, we have to convert 90% into a decimal, and that's just 0.90. So that is our multiplier B. And because it's less than 1, we sometimes call it a decay factor.
And now we just put the pieces together. We have A equals 25,000 and B equals 0.90. So our final function that models the car's value is f of x equals 25,000 times 0.90 to the power of x. With this formula, we can figure out the car's value any year we want.
Okay, fantastic. You've seen how to do it with a table and with a word problem. Now it's your turn to build a function.
Here's a table showing a cougar population that's been reintroduced to an area. Your job is to write the exponential function for this population. So find your initial value A, calculate that constant multiplier B, and then build the equation. Go ahead and pause the explainer right here and give it your best shot.
All right, are you ready? Let's see how you did. The correct answer is y equals 15 times 1.28 to the power of x. How do we get that? Well, the initial value, A, was right there in the table at year 0. It was 15. And to find B, all you had to do was divide 19.2 by 15, which gives you that constant multiplier of 1.28. If you got that, excellent job.
So today you've learned a really important skill, how to look at a pattern of multiplicative change and write the function that describes it. And this isn't just for math class. This applies to finance, biology, technology, so many things. So I'll just leave you with this question. Now that you know how to model growth and decay, what's something in your world that you could predict next?